This is the third dry lab module in the Intro Synthetic Biology online series from CSBIRD. In part 4 of module 2, we saw an introduction to the notion of stochasticity in biology. This module is intended to be a technical introduction to stochastic modeling in biology. References for this module include chapter 7.6 of Brian Ingall's textbook. Again, if you would like to download a PDF of that textbook to follow along, I've included a link in the references slide of module 1. I'll be introducing Gillespie's stochastic simulation algorithm, and for that I reference Dan Gillespie's 1977 paper published in the Journal of Physical Chemistry. I'll also be discussing ways to analytically study the chemical master equation. For this, I reference Andreas Hilfinger et al., published in Physical Review Letter in 2016. For a more advanced textbook reference than Ingall's on stochastic modeling, yet still reasonably accessible, I refer you to an introduction to stochastic modeling by Mark Pinsky and Samuel Carling. This module will begin introducing some basic ideas from probability theory and statistics. This will include discrete and continuous distributions, cumulative distributions, mean and variance, coefficient of variation. And much like how we approach introducing dynamical systems and ODEs, this will not be a rigorous mathematical lecture in probability theory and statistics, but will rather give us a toolbox for applied biological modeling. Then we'll introduce stoichiometry vectors and propensity functions. Then I will introduce the so-called chemical master equation. Following this, we'll be able to discuss Gillespie's stochastic simulation algorithm for simulating stochastic chemical networks. And then I'll discuss some analytical techniques for studying the chemical master equation. Then we'll end with an example calculating the relative noise in constitutive stochastic gene expression. Now we'll move on to Chalk Talk, where we will proceed through the lecture outline that was just presented, resulting in the development of a framework for stochastic modeling of biochemical networks.
We now begin our introduction to stochastic modeling of biochemical systems. Following the slide presentation introducing the notion of stochasticity in biology at the end of Module 2, we will develop a framework now for modeling and studying stochastic biochemical networks. As opposed to considering continuous concentrations of chemical species, as we did in our deterministic modeling, we now consider discrete changes in the abundance of chemical species, that is, the number of molecules of a given species. Our state vector is then the vector n in In, where small n is the number of distinct chemical species in the network, and n sub I, the ith component of the state vector, represents the integer number of molecules of the ith species at a given time. I'll now introduce stoichiometry vectors and propensity functions. Suppose that there are capital K reactions in some network. Each of these reactions is characterized by a stoichiometry vector, S sub k, and a propensity function, R sub k, which is a function of the state vector n. Propensity functions in stochastic modeling are analogous to deterministic rate functions, and the principles of mass action, the Michaelis-Menten kinetics, and transcription factor kinetics from deterministic modeling still apply here in the stochastic setting. Note that by definition, the jth component of the stoichiometry vector tells you how the abundance of species J changes in reaction K. I'll denote the jth component of the stoichiometry vector S sub k as S sub k in round brackets with a subscript J on the outside of the brackets. Right away, let's see an example to try to understand how we formulate stoichiometry vectors and propensity functions. Our example is a simple two-reaction network where reaction R1 has A and B, two different species, combining to form a complex C. The second reaction R2 shows complex C undergoing first-order degradation. For R1, we can see, as I said, that one molecule of A and one molecule of B combine to produce a molecule of C. Therefore, the components of the stoichiometry vector that correspond to components A and B are both -1 to reflect that A and B are consumed in the reaction in step sizes of 1. On the other hand, the component corresponding to the molecule C in the stoichiometry vector is +1, reflecting the fact that one molecule of C is produced in reaction 1. It should now be relatively clear that the stoichiometry vector for reaction 2 is the vectors 0, 0, -1. The two zeros reflect the fact that species A and B are unaffected by reaction 2, and the -1 in the third component reflects the fact that when reaction 2 occurs, one molecule of C is removed from the system. For an arbitrary network, when reaction K occurs, the state vector is updated according to the rule n goes to n plus the stoichiometry vector. Thus, returning to our example network, we suppose that R1 occurs when the state vector n equals 12, 3, and 4, indicating that there are 12 molecules of A, 3 molecules of B, and 4 molecules of C present. Then the state vector after the reaction takes place, if we apply the rule that the state becomes the state vector before the reaction plus the stoichiometry vector for the reaction, then we have that the new state vector is 11, 2, and 5 after adding the stoichiometry vector to the state before the reaction occurred. Now we'll construct the propensity functions for the two reactions in our example network. We can immediately apply the mass action principle that we learned in deterministic modeling. Therefore, the propensity function for the reaction 1 is denoted with little r sub 1, and it's equal to some constant k sub 1, which is a rate constant or kinetic parameter, times the abundance of A times the abundance of B. This follows directly from the mass action rate law. Similarly, the propensity function for reaction 2 follows directly from mass action as well, and we have some rate parameter k sub 2 times the abundance of C. There's a small caveat in constructing mass action propensity functions for stochastic reactions that we didn't need to worry about in the deterministic setting. This is due to the fact that a constraint arises because we are now considering individual molecule numbers rather than concentrations. Consider a reaction such as the one depicted here, where we require 2 molecules of A to make a molecule of C. Since 2 molecules of A are required to make a molecule of C, the propensity to make a molecule of C should be exactly 0 if we have less than 2 molecules of A present. This should be relatively intuitive. So the mass action propensity function for the reaction above is some rate constant K times the abundance of A times the abundance of A minus 1 in order to satisfy the intuitive constraint just described. Shown here is a general formulation of the mass action rate law for stochastic reaction modeling. Note that this formulation satisfies the restriction that if there are less molecules present than the number of molecules needed to participate in a reaction, then the propensity must be 0. At the bottom of this slide, I define some notation that you may or may not already be familiar with. The pi notation denotes a product, similar to the sigma notation for summations. And a number A followed by an exclamation mark denotes a factorial, and we can define a factorial in terms of the pi product notation. And the alpha sub k is a kinetic parameter with units of 1 over time. Consider a small time interval, delta t, and suppose the following. At most, one reaction can occur within the time interval delta t. This follows by allowing delta t to be sufficiently small. And further suppose that the probability that reaction K occurs in time interval t to t plus delta t for some time t is given by the propensity function times the length of the interval, which is delta t. In other words, propensity functions define the probability per unit time of a reaction occurring given the state vector n. You could formulate this in terms of conditional distributions by saying that the probability of reaction K occurring in the time interval t to t plus delta t given the state vector n is equal to the propensity function evaluated at the state vector n times delta t. Our goal is to describe the time evolution of the joint probability distribution P of the state vector at time t. This is a joint probability distribution over the abundances of the n species we consider in our network. Suppose we know the joint probability for some time t. We can describe the distribution at a later time t plus delta t based on the two assumptions above, as is shown here. We can understand this equation intuitively by considering ways in which you could be in state n at t plus delta t. I will now enumerate the different ways in which that can occur. One such way is if at time t you are already in state n and no reactions occur in the interval t plus delta t. The probability to be in state n at time t is given by the joint probability p of nt. The conditional probability of no reactions occurring in the time interval t to t plus delta t given the state n is 1 minus the sum over the product of the propensity function evaluated at state vector n times the length of the time interval delta t. That is shown here. The product of this conditional probability with this joint probability gives the combined probability of being in state n and no reactions occurring in the time interval t to t plus delta t. The other term represents all the ways you could enter state n from another state in the time interval t to t plus delta t. In order for this to occur, you have to be in a state n minus s sub k, where s sub k is the stoichiometry vector for reaction k, and reaction k has to occur in the time interval delta t. This product inside of that sum exactly represents that combined probability, and we sum over all reactions to represent the number of different ways in which you could enter the state n. Thus, these two probability terms represent the total probability to be in state n at time t plus delta t, given that we know the joint probability at time t. Rearranging our equation from the preceding slide slightly, we have the equation that's shown at the bottom here. To get from the top equation to the bottom equation, it's just simple algebra. And now taking the limit that delta t goes to 0 of the left-hand side, we obtain the time derivative of the joint probability distribution. This follows from the definition of derivative. We've therefore derived a differential equation for the time evolution of the distribution of states. This is shown here in the boxed equation, and this is referred to as the chemical master equation in physical chemistry and biological modeling. However, it's a very general equation describing any spatially homogeneous, continuous time, discrete state Markov process, and can simply be referred to as the master equation. The master equation can be understood intuitively by writing it in the form shown here, where we see that the time derivative of the joint probability distribution is a sum over terms representing the flow into the state minus the flow out of the state. Though we refer to this as an equation, there is in fact one such equation for each distinct value that the state vector n can take. It's thus a system of equations where the number of equations is the number of distinct values that the state vector can adopt. And when modeling chemical reaction networks, there's an infinite number of values the state vector may take on, since each species may take on any non-negative integer value in its abundance, and there is a non-zero probability of doing so for each non-negative integer. And of course, there are infinitely many non-negative integers. Moreover, these equations are coupled since the time evolution of the joint probability distribution for a given state vector depends on the joint probability for other state vectors. This can be seen by looking at the first term, representing flow into the state n. It depends on n minus some stoichiometry vector. We have therefore argued that the chemical master equation represents a system of infinitely many coupled differential equations. For this reason, in most cases, the chemical master equation is analytically intractable. There are some exceptions, such as for certain one-dimensional networks where the state vector is actually just a single integer number. If you're curious, see 1D birth-death processes in Pinsky and Carlin's Stochastic Modeling textbook. We'll now consider computational approaches for studying the chemical master equation. The computational approach that we'll focus on is Gillespie's stochastic simulation algorithm. This is a Monte Carlo method, which basically means it's a computational algorithm which relies on random sampling. And this algorithm uses the chemical master equation to generate sample trajectories of chemical reaction networks. Some applications are calculating the time-dependent statistics on an ensemble of many generated sample trajectories, or estimating the stationary distribution, P steady state, which solves the time derivative of the joint probability distribution set equal to 0, in other words, setting the master equation equal to 0. Note that in the latter case, one may take advantage of the fact that in general, Markov processes describing biochemical networks will asymptotically converge to the stationary distribution of the process. This is similar to how solutions to ODE models of chemical networks typically converge to a unique stable fixed point. In other words, generally we can assume that the limit as time goes to infinity of the time-dependent joint probability distribution equals the steady state distribution, which solves setting the master equation equal to 0. Using this, the stationary distribution, or its statistics, may be estimated from a single trajectory as long as it's run for a sufficiently long time. We'll now develop the algorithm and end with stating the pseudocode for implementing the algorithm. The stochastic simulation algorithm, or Gillespie's algorithm, depends on two random variables, which are generated computationally using pseudo-random number generators. We won't get into the math or computational science behind pseudo-random number generators, but just know that most scientific computing programming languages have built-in random number generators that you can use relatively easily to sample uniformly distributed random numbers. Many languages also have means to sample random numbers from other common distributions, such as exponential distributions or Poisson distributions. But we will consider just using uniformly distributed random numbers, and we will transform those random numbers to be distributed according to different distributions as we require. The two random variables that the algorithm relies on is the time capital T between consecutive reactions and the reaction R that occurs. We will now discuss how to determine these. After doing so, we'll be able to enumerate the steps for implementing the algorithm. Let P of R equal R sub k be the probability that the next reaction to occur will be R sub k in a network of an arbitrary number of reactions, capital K, given the current state vector. The probability that the next reaction will be R sub k ought to be proportional to its propensity function, lowercase r sub k, evaluated at the current state, as this prescribes a probability per unit time of the reaction R sub k to occur for a given state. Using this, we can write that the P of R equal R sub k is equal to the propensity function for the kth reaction evaluated at the current state, divided by some normalization factor. The normalization factor will need to satisfy the normalization condition for a discrete distribution. That's shown here, where we have the sum over all states of the probability for each state has to equal 1. Carrying out the algebra imposed by this condition, we solve for the normalization factor z, as is shown here, and it turns out to be the sum over all reactions of the propensity function for each reaction evaluated at the current state. Putting this all together, we have the expression shown at the bottom for the marginal probability distribution for the next reaction to occur given the state n. In order to implement the algorithm, we need to know how to sample the R sub k's from this distribution that we've developed. A marginal distribution, such as P of R equal R sub k from the preceding slide, can be thought of as a partitioning along the unit interval, that is, the numbers between 0 and 1, including the endpoints. Probabilities must add to 1, and thus the probability of reaction R sub k occurring represents a subinterval of length P of R equal R sub k, which ought to be less than 1, of the unit interval. We can easily use built-in pseudo-random number generators in our favorite scientific computing language to generate uniformly distributed random numbers. I'll denote these U, and these will be uniformly distributed over the unit interval. The reaction we pick is R sub I, such that U is less than or equal to the probability of R sub I occurring, and at the same time, U is greater than the probability of R sub I minus 1 occurring, unless I equals 1. This can be summarized as is shown below. The only thing left to determine in order to implement the Gillespie's algorithm is how to sample waiting times between consecutive reactions. Note that while R, the reaction to occur, is a discrete random variable, the waiting time t is a continuous random variable. Recall that the propensity function gives the probability per unit time of a given reaction to occur, given the current state. The probability of no reaction occurring in a small time interval, delta t, is therefore 1 minus the sum over the propensity functions for all reactions evaluated at the current state times the time interval delta t. Similar to how we derived the chemical master equation, we may write the equation shown here for the conditional probability of no reaction occurring in some time interval given the current state. The probability of no reaction occurring in a time interval of length t, given the state n, and the probability of no reaction occurring in a time interval of length delta t, given state n, are independent. Therefore, this equation above follows from the fact that given two random variables a and b, the probability of a and b is equal to the probability of A times the probability of B. We're using the fact that the probability of no reaction occurring in a time interval of length t plus delta t is the same as the probability of no reaction occurring in time interval of length t and no reaction occurring in the time interval of length delta t. Then using the rule for independent probabilities previously mentioned, we have that the probability of no reaction occurring in time t plus delta t has to equal to the probability of no reaction occurring in time t times the probability of no reaction occurring in time delta t. And that is exactly what the two terms on the right-hand side of this equation represent. Note, all of these probabilities are conditioned on the state n. I've omitted saying that in several cases just for clarity. Now, rearranging this expression slightly and taking the limit that delta t goes to 0 while invoking the definition of a derivative, similar to how we did in deriving the chemical master equation, we obtain the following differential equation for the conditional probability that no reaction occurs in a time interval of length t given the current state. This differential equation says that this conditional probability's derivative with respect to time is proportional to the conditional probability itself. Therefore, it has exponential solutions, as is shown below. The z shown here, again, is a normalization factor that we need to determine. And just a quick note on my notation, exp of x, where x is a real number, is just e to the x. So we see that the waiting time t is exponentially distributed. And we still need to solve for the normalization factor, as I previously mentioned. We do so by imposing the normalization condition for continuous distributions, which is shown here. The condition is that the integral of the probability distribution over all states of the distribution needs to equal 1. Here, we have just substituted our expression for p sub 0 of t. And in the next line, we can use the fact that z is a constant with respect to t, and therefore we can pull it out of the integral to solve for it, which is shown here. And then we simply compute the integral shown here, and it turns out that z takes this form. Now substituting z back into the expression for p sub 0 of t, we have this final expression for our conditional probability distributions of waiting times given current state. To sample the waiting times, t, we will make use of what's called inverse transform sampling, and the fact that we can easily sample uniform random numbers on the unit interval. In what follows, I will discuss inverse transform sampling in some detail. Suppose we could find a monotonic transformation, denoted by this curly t, that maps values from the unit interval to the real numbers. Additionally, we'll want this transform to be such that evaluating it on a uniformly distributed random number u on the unit interval equals to a value t, where t has the desired cumulative distribution function. The definition of a cumulative distribution function is the probability for the random variable adopting values in some interval. In this case, we consider the interval to be 0 to some lowercase time t. We calculate this based off its definition as the integral over 0 to t of the marginal distribution. The marginal distribution I refer to is the distribution previously developed for the waiting time. If we assume we have such a transformation, then the line shown here follows directly by applying the transformation on all values that appear in the first expression here. We further have to assume that the inverse transformation evaluated at 0 is equal to 0. Now we'll use the fact that the cumulative distribution function for uniformly distributed random variables on the unit interval has this form. This should be pretty intuitively clear that this is the cumulative distribution for uniformly distributed random numbers. If you don't buy it, I encourage you to compute the cumulative distribution for uniformly distributed random numbers using the definition. Using this, we conclude that this value from up here, shown down here, is equal to the inverse transform evaluated at lowercase t. Again, this follows directly from this fact about the cumulative distributions for uniformly distributed random numbers, and the fact that the inverse transform evaluated at any number lowercase t is less than or equal to 1, and this follows from the fact that the domain of the transform t is the unit interval, and therefore all values in the codomain of the inverse transform are between 0 and 1. We established two things on the preceding slide. The first thing is that the cumulative distribution for the waiting time capital T to be between 0 and lowercase t is equal to the cumulative distribution for the uniformly distributed random number u to be between 0 and the inverse transform evaluated at lowercase t. That's shown here in this equation. The second thing we established on the preceding slide is that the right-hand side of this equation is equal to the inverse transform evaluated at lowercase t. Putting these two equations together, we have this expression for the cumulative distribution of the waiting time t in terms of the inverse transform evaluated at lowercase t. Now we need to note that the cumulative distribution function is actually a function of lowercase t. For notational clarity, I'll now define explicitly a function, capital F, of lowercase t that is equal to the cumulative distribution function for the waiting time, capital T, to be between 0 and lowercase t. Now, inverting both sides of this equation is equivalent to writing that the inverse function of the cumulative distribution function f, evaluated at the uniform random number u, is equal to the transformation t evaluated at that random number u. But recall from the beginning that the transformation curly t evaluated at the uniformly distributed random number u is equivalent to the waiting time t by assumption. So if u is the random number, uniform random number we sampled, then we can take the waiting time t to be the inverse of t's cumulative distribution function evaluated at the uniform random number u. Our discussion on inverse transform sampling has led us to conclude that we're able to sample exponentially distributed waiting times from uniformly distributed random numbers using the inverse cumulative probability distribution function. Now, it remains for us to explicitly calculate this cumulative distribution function, and we will do this directly from the definition previously mentioned in terms of the integral over the marginal distribution. Now, we simply just need to plug in our expression for p sub 0 of t that we previously obtained and compute the integral. In doing so, we see that the cumulative probability function for the waiting times t takes the form of 1 minus e to the minus sum over all propensity functions evaluated at the current state times the time t. Note, lowercase time t is the argument which the cumulative probability function takes. And so f of t is exactly equal to this. Now we need to invert f in order to apply our inverse transform sampling rule. Let y equal f of t, which is equivalent to what is shown here based on the preceding calculation. And then we have that the exponential of this sum over propensity functions times time is equal to 1 over y. This just follows from some simple algebraic manipulations, taking the exponential to the other side and the y to the other side. Now we take the natural log of both sides, and we have this expression. Now we divide both sides by minus the sum over the propensity functions. And now we have an expression for lowercase t in terms of y. Now, if y is uniformly distributed on the unit interval, then so is u defined as 1 minus y. Therefore, given a random number u sampled from the uniform distribution on the unit interval, we can transform to exponentially distributed weighting times t via the inverse transform formula shown here. Note that since u is less than or equal to 1, the logarithm of u will be negative, and therefore the minus sign out front makes sure that our times are positive, given that the propensity functions are necessarily positive. To summarize what we've done pertaining to Gillespie's algorithm, I will now show the pseudocode for implementing the algorithm. First, you set the initial state and initialize time to have a value of 0. Then, calculate the reaction propensities at the current state based on the functional form of the reaction propensities for each k. Then, you sample a uniformly distributed random number u from the unit interval and choose the reaction R sub k to occur according to the rules that we developed, and they are summarized here. Then, you sample another uniformly distributed random number from the unit interval and use the inverse transform sampling formula that we just detailed. This gives an exponentially distributed weighting time t. Then, we update the system time by taking the current time t to t plus capital T being the waiting time. Then we update the state vector by taking the state vector n before the reaction occurred to the state vector n plus the stoichiometry vector for the reaction k that has occurred. Then you return to step 2 until sufficiently many iterations of the algorithm have occurred. And what is sufficient will depend on what the system is that you're studying and also what you wish to study about the system. For example, are you computing long time statistics to approximate the steady state distribution statistics, or are you computing time dependent statistics over many trajectories? I'll now discuss some analytical techniques for studying the chemical master equation. Consider the general form of the chemical master equation. I've shown the equation here as a reminder. As previously noted, it's difficult and impossible to solve for the full joint probability distribution in general. So we'd like other ways to study the nature of solutions to the chemical master equation. We previously introduced computational methods for studying these, but we'd also like some analytical techniques. In experiments, one is typically only interested in first and second order moments. First order moment being a mean, for example, and the second order moments being variances and covariances, for example. The question we ask is, can we say anything about the stationary first and second order moments without solving the chemical master equation? I'll now discuss statistical invariants that follow from stationary means. The average abundance of species I at time t is given by the expression shown here, where the angle brackets denote ensemble averages, and the right-hand side is just the definition of an average given a probability distribution P of n. Time dependence comes from the fact that I've written the time-dependent probability distribution in the sum. If, on the other hand, I had written the stationary distribution, which is time-independent, then, of course, the average would in turn be time-independent as well. And just a quick note on how we obtain the marginal distributions P of ni from the joint distribution. The marginal distributions are obtained by summing out the dependence on all other abundances other than the abundance which we are concerned with. For example, if we want the marginal distribution P of ni, Then we run a sum over an index j, where j takes on all values from 1 to n, where n is the number of species, except for the value I, which is the species whose abundance distribution we care about. And then within this sum, we run a sum of the abundance of species j from 0 to infinity, that is all values that species j abundance can take. And within that sum, we have the joint distribution. This computation effectively integrates the dependence on all other species abundances other than species I abundance n sub I. Now, on our way to deriving a statistical invariant that follows from stationary averages for an arbitrary n-dimensional network, we're going to need to derive a differential equation for the average abundance of each species in that network. Before indicating the expressions for these differential equations, let us derive the differential equation governing the average abundance of a single component in a one-dimensional network. We therefore consider the one-dimensional master equation shown here. The reason for doing this is mainly pedagogical, given that the derivation in one dimension is more transparent due to its simplicity compared to the derivation in n dimensions, but we will discuss the generalization to n dimensions following the one-dimensional derivation. Immediately from the definition of averages and the linearity of differential operators allowing us to bring d by dt inside the sum, we can write this expression for the time derivative of the average abundance of the single species in our one-dimensional network. Note that because n is a random variable and therefore does not have explicit time dependence, we don't have to worry about acting the d by dt on the n, and therefore when it comes inside the sum due to its linearity, we acted just on the distribution. Now, using the master equation to substitute about the expression for dp by dt, we have what is shown on the right. Now I will switch the order of the sums. That is, the sum over k is going to come to the outside, and the sum over n will be inside of that. Those who are a little more mathematically inclined are worried if this is allowed, because it's not always in general. See Fubini's theorem for sums. The conditions of the theorem are satisfied here if the average exists, which we can assume it does. So the theorem tells us the sums commute. So commuting the sums, as I said I would, I have this expression here. For each k, the terms of the first inner sum is identically 0 if n is less than s sub k, since the probability of n taking a value less than 0 is 0. And indeed, if n was less than s sub k, we would have p of an abundance less than 0. Now, define the variable n prime as n minus s sub k. It's equivalent to saying that n is equal to n prime plus s sub k. Now, we can manipulate the sum as is shown here. We're taking this sum here from the top expression, so it's right here, and using the fact that p at n less than 0 is identically 0, I can run the sum from n equals sk to infinity rather than n equals 0 to infinity, since all of the terms for n less than s sub k are 0 and contribute nothing to the value of the sum as a result. Then I can use the definition of n prime to index my sum from n prime equals 0 to infinity. Here I've substituted directly the n equals n prime plus sk, and also the n prime equals n minus sk. Therefore, I can replace n minus sk in the probability distribution with n prime, similar to the argument of the propensity function. But this expression shown here, after distributing the sum here, is equal to this. And then noting that this is indeed equal to this, given that that's what we started with here to obtain this expression, then we can cancel off this sum over the n prime with the sum over n here, because they're identical, except we've used a different value for the index of the sum, but that doesn't matter. And now all that's left is this inside the sum over k. So finally, our expression for the time derivative of the average abundance is given by this. We can define the average flux of molecules entering the system and the average flux of molecules leaving the system by the two respective expressions here. Note that the average flux of molecules entering the system are all of the terms of this sum for which S sub k is positive. Similarly, note that the average flux of molecules leaving the system are all the terms of this sum for which the S sub k is less than 0. As well, the S sub k are taken in absolute value in both equations, and so this expression is actually equal to the average flux of molecules entering the equation minus the average flux of molecules leaving the equation, leaving the system. And then, using the fact that on the previous slide we showed that the time derivative of the average abundance was exactly equal to this sum, we can then write the time derivative of the average abundance in terms of average fluxes of molecules entering and leaving the system. And it turns out that this generalizes nicely to the multi-species case, or the arbitrary n-dimensional case, where we have that the time derivative of the average species abundance for species I is equal to the average flux of molecules of species I entering the system minus the average flux of molecules of species I leaving the system. This is true for any species in the network. And the definition of average flux generalizes rather simply, as is shown here. The only difference is that we need to put an index on the stoichiometry coefficient. And as well, the state variable becomes a state vector. As previously mentioned, one is often interested in the stationary distribution. Stationary distribution is defined as the distribution which solves the master equation set equal to 0, and it follows that all of the statistical moments are also constant in time. Thus, for a stationary distribution, we have what's called flux balance. That is, the average flux of molecules of species I entering the system is equal to the average flux of molecules of species I leaving the system for every species in the system. The fluxes in and out of the system will in general be functions of some statistical moments. Which statistical moments depends on the functional form of the propensity functions, but flux balance enables one to relate stationary averages to other stationary averages and/or kinetic parameters. In the case of networks with only unimolecular reactions, the stationary averages that show up in the flux balance equations will be stationary average abundances of various network species. For networks with higher order reactions, the flux balance relationships will depend on higher order statistical moments. I'll now derive statistical invariants that follow from stationary variances and covariances. The variance of the abundance of species I, var of Ni, is computed as shown here by the definition of variance being the average of delta Ni squared, where delta Ni is defined as Ni minus the average of Ni. In the time-dependent case above, this should be the time-dependent average, but if we are calculating the variance over the stationary distribution, then of course this should be the stationary average. Similar to how we wrote down a differential equation for the average abundance before, we now write down a differential equation for the variance. And again, I'm going to work with the one-dimensional master equation for right now, and we'll discuss generalizations to the n-dimensional case afterwards. Following a very similar procedure to how we obtained an expression for the time derivative of the average abundance in the one-dimensional case, one may determine a differential equation for the variance of the abundance in the one-dimensional case, and it turns out to have this form. Now, taking this at stationarity, we can set the left-hand side equal to 0, and therefore we can take this term to the left-hand side and write the equation like this. Note that the sum over k, where k indexes the reactions of the stoichiometric coefficient S sub k times the propensity function R sub k evaluated at the abundance n, is equivalent to the flux in minus the flux out of the system by definition of these fluxes. Therefore, the sum is simply the net flux of molecules into the system. Or, if it's negative, net flux of molecules out of the system. Now, substituting this relation into the left-hand side of this equation, we obtain this equation. Now, we introduce covariance as a measure of the joint variability of two random variables. In general, the covariance between two random variables x and y is defined as the expectation or the average of delta x times delta y, where the deltas are defined similarly to how we defined delta n. Now, that by flux balance, we have the delta of J minus minus J plus, which is equivalent to J minus minus J plus minus the average of J minus minus J plus. This is exactly equal by flux balance to J minus minus J plus. This is because this average is exactly 0. This follows from acknowledging the linearity of taking averages, so that the average of J minus minus J plus is equal to the average of J minus minus the average of J plus, and flux balance tells us that those two averages are equal, therefore their difference is equal to 0. And so we have this expression for delta J minus minus J plus at stationarity. And so the covariance between the abundance n and the difference of the flux out minus the flux in, which is by definition the average of the delta n times the delta J minus minus J plus, is equal to the average of delta n times the difference between J minus and J plus. This just follows by substituting the above expression for delta J minus minus J plus into the expression here for the covariance. But we've shown on the preceding slide that the variance time evolution equation at stationarity implies this relationship. Now, substituting this relationship into the expression for the covariance we're considering above, we have that 2 times the covariance between the abundance n and the difference between J minus and J plus is equal to the average of the sum over all reactions of the stoichiometric coefficient squared times the propensity function. And it turns out for multi-species networks, we can actually derive the following relationship for any 2 species, I and J, in the network. That is, the covariance between the abundance for species I and the difference between the flux out of the system for species J minus the flux into the system for species J, plus the same term with the indices permuted. That is, we're considering nj rather than ni, and j plus minus of I instead of n plus minus of j. The sum of these two terms is equal to the average of the sum over all reactions of the product of the stoichiometric coefficients for each of I and j times the propensity function. And in the case that I is equal to j, it reduces to the expression that we had in the preceding slide from the one-dimensional network. Admittedly, this is quite a bit more complicated than the flux balance expression and a little more difficult to understand intuitively. But we'll see that this mathematical relationship turns out to be useful in quantifying noise in biochemical networks in an example that follows. The example we'll consider is quantifying noise in unregulated stochastic gene expression. Recall the mRNA protein model of constitutive or unregulated gene expression that was previously introduced in the Introduction to Deterministic Modeling of Gene Circuits. Denoting the mRNA and protein as capital M and capital P and their abundances as lowercase m and lowercase p, respectively, the reactions and corresponding propensities are shown below. We have transcription, which is the process of creating mRNA, and this takes place with a constant propensity function due to the fact that we're considering constitutive or unregulated gene expression. Then we have the translation process, which is the conversion of mRNA to protein. Using mass action kinetics, our propensity function is proportional to the mRNA abundance, as is shown here. Then we have the two decay terms. Both of these decay terms have propensity functions that are proportional to the abundance of the species that is being degraded. That is, the propensity function for mRNA decay is some rate constant times the mRNA abundance, and the propensity function for protein decay is some rate constant times the protein abundance. This is very similar to what we did in modeling decay due to macromolecular degradation and dilution when we considered deterministic models of gene circuits. Before computing an expression for the noise in constitutive gene expression using the statistical invariants that we derived, let's have a brief digression on quantifying noise in general. When analyzing stochastic biomolecular networks, one is often interested in the noise in the system at stationarity. From here on, all averages and variance that I write can be assumed to be taken at stationarity. The coefficient of variation for a random variable x is defined as the square root of the variance of x divided by the average of x. We denote the coefficient of variation for x as CV subscript x. This is a dimensionless measure of noise. One may equivalently consider the squared coefficient of variation as a dimensionless measure of noise. Furthermore, we may be interested in the size of covariations relative to the average abundances. Let us define such a measure as eta subscript xy. We define eta subscript xy as the covariance between random variables x and y divided by each of their averages. Note that if x equals y, then eta xx or eta xy equivalently is equal to the squared coefficient of variation for x or y. We may use the flux and covariance balance equations to derive an expression for eta mm, which is the mRNA noise. Recall the covariance balance equation shown here. Now we can plug in the propensities and stoichiometric step sizes, which in this case are all 1, although if you're interested, see pages 245 to 246 for a brief discussion on bursting in gene expression. These pages are references to Ingall's textbook. Now, if we plug in the propensities and stoichiometric step sizes into this general covariance balance equation above, we obtain this expression. 2 times the covariance between M and beta sub m times m minus the constant k sub m is equal to the average of k sub m plus beta sub m times m. Now we'll use some basic results from statistics to simplify the expression from the previous slide. As previously noted several times, averaging is a linear operation. So the average of k sub m plus beta sub m times m is equal to the average of k sub m plus the average of beta sub m times m. Note that the average of a constant is just the constant itself, and the average of a constant times a random variable is the constant times the average of the random variable. We'll also use the fact that the covariance of a random variable with a constant is zero. I will also use the fact that the covariance of a random variable x with itself is equal to the variance of x for any random variable x. I've already implicitly used this when I stated that eta sub xx is equal to the coefficient of variation for x. And the other thing we'll use is that the covariance of x with another random variable times a constant is equal to that constant times the covariance between x and the other random variable. Using these notions from statistics, we have the relationship shown here. This is what we had from the previous slide, and invoking all of these, we can simplify it to what's shown here. Additionally, flux balance implies that k sub m is equal to beta sub m times the average of m. Now, substituting k sub m equals to beta sub m times the average of m, we have that the variance of m is equal to the average of m. And it turns out that the mRNA in constitutive gene expression is distributed according to what's called a Poisson distribution, which has variance equal to its average. Therefore, eta mm equals 1 over the average of m. In other words, as the mRNA abundance increases, the fluctuations in mRNA decrease as 1 over the average. Now, I'll leave it as an exercise to show that the protein noise for unregulated stochastic gene expression turns out to be the following expression. We have eta sub pp is equal to 1 over the average of p plus this time averaging term times 1 over the average abundance of mRNA. Note, I define average lifetimes of a molecule of species I at stationarity as tau sub I, and it can be expressed as the average abundance of species I divided by the average flux in and out of the system of species I. Note that at stationarity, the average flux in is equal to the average flux out. This expression for average lifetime is known as Little's law and is a well-known result in queuing theory. This expression for the protein noise can be obtained similar to how we obtain the expression for mRNA noise, using just covariance and flux balance. The only additional thing we'll need is the definition of average lifetimes given above. I strongly encourage you to try to work this out to test whether you understand these statistical invariants and their application in quantifying noise in gene networks, but it's up to you. That concludes the third and final module that I'll be giving, and now I'll just summarize what we covered. Covered propensity functions and stoichiometry vectors. Then we looked at Markovian models of chemical networks and introduced the chemical master equation. Then we discussed Gillespie's stochastic simulation algorithm. This includes how we sample reactions, inverse transform sampling for exponential waiting times, and the pseudocode for implementing the algorithm. If you've never implemented this algorithm before or you're not familiar with it, then perhaps it might be a good exercise for you to implement it in your favorite scientific computing language for some example system. For example, you could implement it for the constitutive gene expression model. You could then compare your numerical statistics with the expressions for noise obtained on the previous few slides, as well as the averages predicted from flux balance. You could then also look at how the accuracy of your stationary statistics as numerically obtained from the Gillespie algorithm change as you change the number of reactions. Then we looked at analytical techniques for studying the chemical master equation. This mainly focused on statistical invariants that follow from stationary means, variances, and covariances. Then we ended with an example where we used these statistical invariants to quantify noise and constitutive gene expression.